In episode 26, titled Simulation Thinking, Monte Carlo for Uncertainty and Risk, the goal is to use Monte Carlo thinking to estimate outcomes under uncertainty, because DataX scenarios often ask you to reason when the world is noisy and exact formulas are either unavailable or not worth the effort. Simulation is not a shortcut for avoiding rigor. It is a structured way to propagate uncertainty through a model and understand the range of plausible outcomes. When you use Monte Carlo well, you stop speaking in single-number predictions that create false certainty and start speaking in probabilities, ranges, and confidence bounds that support responsible decisions. The exam rewards this mindset because many real data problems involve messy distributions, dependent factors, and policy choices under risk appetite. In this episode, you will learn what Monte Carlo means, when it is appropriate, and how to narrate a simulation loop clearly without needing to type anything. You will also learn how to summarize results in ways that reveal tail risk rather than hiding it under an average. The goal is to make simulation feel like a professional reasoning tool you can explain and defend. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Monte Carlo simulation is repeated random sampling used to model variability, which is a plain English way of saying you generate many possible versions of the world and see how outcomes change. You start with uncertain inputs, such as demand, latency, failure rates, costs, or detection rates, and you represent that uncertainty with distributions rather than fixed values. Then you draw random samples from those distributions many times, each draw representing one plausible future scenario, and you compute the resulting outcome for each scenario. By aggregating those outcomes, you can estimate not only the expected result, but also the spread, the tail behavior, and the probability of crossing important thresholds. The exam usually does not require you to implement simulation, but it does expect you to understand what it does and why it is useful. Monte Carlo is especially helpful when you cannot write down a clean formula for the outcome distribution because inputs interact in complicated ways. When you can describe Monte Carlo as repeat random draws to see outcome variability, you are already thinking the way the exam expects. A practical reason to use simulation is that many real-world problems have formulas that are hard, fragile, or full of assumptions that do not match reality. If outcomes depend on multiple uncertain inputs, nonlinear relationships, or conditional rules, analytic solutions can become complicated quickly. In those cases, trying to derive a closed-form answer can be slower and less trustworthy than simulation, especially if the assumptions needed for a clean formula are unrealistic. The exam may describe a decision problem with several uncertain factors, like cost, adoption, incident rates, and staffing constraints, and the correct approach may be to estimate the distribution of outcomes rather than chasing an exact point estimate. Simulation also lets you incorporate realistic distribution shapes, such as skew and heavy tails, which are often ignored in simple formula approaches. This is consistent with DataX's emphasis on judgment and realism, because a method that respects uncertainty and shape can produce better decisions than a method that produces a neat but misleading number. When you recognize that formulas are hard or assumption-heavy, simulation becomes a defensible option. Choosing input distributions is where Monte Carlo either earns trust or loses it, because the quality of the output is constrained by the quality of the assumptions you feed in. Inputs should be based on process knowledge and evidence, meaning historical data when available, domain expertise about plausible ranges, and awareness of tail behavior. For example, if you are modeling latency, you might choose a skewed distribution rather than a symmetric one, because latency often has a long right tail. If you are modeling failures, you might use a rate-based distribution for counts over time, reflecting the process that generates incidents. The exam may ask what you should do before simulating, and a strong answer emphasizes selecting distributions that match the data-generating process and validating them against observed patterns. You do not need perfect distributions to gain insight, but you need defensible ones, because simulation is not magic. DataX rewards learners who treat distribution selection as a modeling decision grounded in evidence, not as a convenient guess. Dependencies are another critical consideration because naive independent sampling assumptions can break simulation realism and produce overconfident results. Many uncertain inputs move together, such as demand and load, or attack volume and false alarm rates, or economic conditions and churn behavior. If you assume independence when variables are correlated, you can understate risk by failing to generate scenarios where multiple bad things happen at the same time. The exam may describe linked factors or shared drivers, and the correct response often involves acknowledging dependence and modeling it appropriately. Even without formal correlation structures, you can represent dependency by sampling shared drivers first and then generating dependent outcomes from that shared context. This is a judgment skill, and DataX rewards it because it reflects real-world thinking about systemic risk rather than isolated variability. When you can say that simulation must respect dependencies to avoid false confidence, you demonstrate mature understanding of uncertainty modeling. A useful exercise is narrating one simulation loop in plain language, because that is the simplest way to show you understand how Monte Carlo works without needing a keyboard. Start by defining the inputs as distributions. Then describe drawing one sample from each distribution, which represents one plausible scenario. Next, describe applying the decision rule or model to those sampled inputs to produce one output, such as total cost, number of incidents, revenue outcome, or workload estimate. Then describe storing that output and repeating the process many times, producing a collection of outcomes that represent many plausible futures. Finally, describe summarizing those outcomes to understand expected performance and risk of bad outcomes. This narration mirrors how you would implement it, but it keeps the focus on logic rather than on code. The exam rewards this mental model because performance-based questions often want you to describe a workflow rather than an implementation. When you can narrate inputs, draws, outputs, and summary, you are demonstrating full comprehension of the simulation process. Summarizing simulation results with percentiles is essential because percentiles reveal tail risk and decision reliability in a way averages cannot. An average outcome can hide the fact that in a substantial fraction of scenarios, outcomes are much worse than expected, which matters for risk management and capacity planning. Percentiles let you say things like, in 90% of simulated futures, cost stays below this value. Or, there is a 5% chance demand exceeds capacity, which are decision-relevant statements. The exam often expects you to reason this way because it ties directly to service-level targets, staffing decisions, and risk appetite. Percentiles also remain meaningful in skewed distributions, where averages can be inflated by rare extreme futures. When you summarize with percentiles, you make uncertainty visible and give stakeholders a way to choose policies based on tolerances. DataX rewards percentile-based summaries because they align with how leaders think about worst-case planning and acceptable risk. Simulation supports interpreting uncertainty as ranges and probabilities, not as single predictions, which is a major conceptual shift the exam rewards. A single-point prediction implies certainty that rarely exists, while a range shows what outcomes are plausible given input uncertainty. Probabilities let you quantify the chance of crossing a critical threshold, such as exceeding a budget, missing a service level, or generating too many alerts. This is especially important when decisions are asymmetric, meaning the cost of being wrong on one side is much higher than on the other. The exam may present a scenario where a safe decision depends on the chance of a bad outcome, and simulation is a natural tool for estimating that chance. Thinking in ranges also helps you compare strategies under uncertainty because you can see which strategy has lower tail risk even if the average looks similar. DataX rewards this because it reflects professional decision support, where uncertainty is acknowledged and managed rather than ignored. Monte Carlo also helps compare strategies under different risk appetites, because it can show how choices trade average performance against tail risk. Two strategies might have similar expected outcomes, but one might have a much worse downside in a small fraction of futures, which could be unacceptable in a high-stakes environment. Another strategy might be more conservative, with slightly worse average performance but much tighter downside, which could be preferred when stability is valuable. The exam may frame this as choosing between options under capacity constraints or compliance risk, and the best answer often involves matching the strategy to the organization's tolerance for rare but severe outcomes. Simulation makes that matching visible by showing the distribution of outcomes for each strategy, not just a single score. This also helps you explain decisions to stakeholders because you can tie the choice to the probability of unacceptable outcomes. DataX rewards this because it reflects leadership judgment under uncertainty rather than simplistic optimization. A key danger is false precision when inputs are guesses rather than measured values, because simulation can produce detailed-looking outputs that are not actually reliable. The output distribution is only as defensible as the input assumptions, and if inputs are speculative, the simulation results should be framed as exploratory rather than definitive. The exam may ask what limitation to communicate, and the best answer often involves acknowledging uncertainty in inputs and avoiding overconfidence in numerical precision. This does not mean simulation is useless with uncertain inputs. It means you use it to explore sensitivity, identify which assumptions matter most, and understand plausible ranges rather than claiming exact probabilities. In professional terms, you treat simulation as a decision support tool that clarifies uncertainty, not as a guarantee machine. DataX rewards this caution because it reflects integrity in analysis, where you communicate what the method can and cannot support. When you state that guessed inputs lead to uncertain outputs and that results should be interpreted accordingly, you are reasoning responsibly. Monte Carlo connects naturally to bootstrapping and model evaluation uncertainty because all three ideas involve using repeated sampling to understand variability. Bootstrapping resamples observed data to approximate the sampling distribution of an estimator, while Monte Carlo samples from assumed distributions to explore future variability. In model evaluation, repeated sampling appears in cross-validation and repeated splits, where you measure how performance varies across different partitions. The exam may test this linkage conceptually, asking how to quantify uncertainty in performance metrics or how to estimate confidence around an evaluation result. Monte Carlo can also be used to propagate uncertainty in model inputs, such as uncertain feature values or uncertain demand forecasts, into uncertainty about model outputs. Recognizing these connections helps you see simulation as part of a broader family of resampling-based reasoning tools. DataX rewards this because it reflects integrated understanding rather than isolated memorization. When you can connect simulation to bootstrapping and evaluation variance, you show you understand why repeated sampling is a powerful pattern across analytics. Communicating simulation findings is ultimately about decision support, not about guaranteed outcomes, and the exam often rewards how you frame results. A good communication approach emphasizes that simulation explores plausible futures given assumptions, and that it provides ranges and probabilities that help choose policies. It also emphasizes what assumptions were made, what dependencies were modeled, and what uncertainties remain, because those details determine how much confidence stakeholders should place in the conclusions. Instead of presenting a single predicted value, you present a distribution and highlight key percentiles, such as the median outcome and the upper tail that reflects worst-case risk. You then tie those outcomes to decisions, such as staffing buffers, budget reserves, or threshold settings, which makes the simulation actionable. The exam may ask how to present results responsibly, and the best answer often includes both uncertainty ranges and clear decision implications. DataX rewards this communication style because it respects uncertainty while still enabling action. A useful anchor for this episode is to remember that you simulate many futures, then choose with confidence bounds because it captures the purpose and the discipline. Simulation is about generating many plausible outcomes, not about predicting one inevitable result, and confidence bounds are how you summarize and act on that uncertainty. The anchor also reminds you to treat results as distributions with percentiles and tail probabilities, which are the decision-relevant outputs. It helps you resist the temptation to overinterpret precise-looking numbers when inputs are uncertain, because you remember that bounds reflect uncertainty, not certainty. Under exam pressure, this anchor can guide you to answer simulation questions in a way that emphasizes ranges, risk appetite, and defensible assumptions. DataX rewards this because it aligns with real-world risk management, where decisions are made with uncertainty acknowledged and bounded. When you can articulate that the value is in the distribution of outcomes and the confidence you can place in policy choices, you are applying Monte Carlo correctly. To conclude episode 26, describe one uncertainty problem and then state simulation steps in plain language, because that is what the exam is looking for in scenario reasoning. Choose a problem like estimating staffing needs under variable alert volume, forecasting cost under uncertain demand, or estimating downtime risk under uncertain failure rates. Then state the steps as defining input distributions based on evidence, modeling dependencies when present, drawing many random scenarios, computing the outcome for each scenario, and summarizing the resulting outcomes with percentiles and tail probabilities. Add the caution that inputs should be defensible and that results should be communicated as ranges and probabilities rather than as single guarantees. Finally, connect the summary to a decision, such as choosing a threshold, selecting a strategy, or setting a buffer that matches risk appetite. If you can narrate that flow clearly, you will handle DataX questions about Monte Carlo simulation with calm, correct reasoning, and professional judgment. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.